Morning, guys. Today's our lesson 7.3D, volume from a known cross-section. This is another application of volumes of an integral. But what it does is it gives you a three-dimensional object. And these lines are slant, not because it's been drawn wrong, but here's my x-axis, here is my y-axis, and what's going to happen is this volume of the cross-section is going to project vertically, and you're going to see what I mean here in a minute. But before we do this, before we go after this, we need to think about some of these formulas that we need to remember of particular cross sections that they are going to ask you about. Okay, because our job is going to be to find the area A of x of a cross-sectional area function, and it'll all come together here. But you know, the first one's a tough one. So if I got a square whose side length is x, that means these are all x. Well, the area is pretty tough. It's x squared. There's my area function. If my cross-sectional, if my known cross-section is a square with the side in the cross-sectional area, okay? And then we have, what is the area of a square if the diagonal is x? Well, so what are they doing? They're telling me here, I know the diagonal of this guy is x. Well, if I have a square and I draw a diagonal, that breaks me into a 45, 45, 90 triangle. And I don't know if you remember from geometry, your shortcut formulas for a 45, 45, 90 triangle, but there was a little formula out there that said the hypotenuse equals the leg times the square root of 2. 2 was your multiplier in a 45, 45, 90 triangle. Because what I need to do is I'm trying to find the area of this square that you see in terms of x. So my area is going to be, well, you know, it's a side squared. Okay, so my area is going to be something squared. But I need to know what is the side lengths of this square if the diagonal is x. Well, the diagonal is my hypotenuse. Well, that means the leg times root 2. Well, that means this is a leg and this is a leg of that 145, 90 triangle. So my leg is going to equal x divided by root 2. So this side is going to be x over square root of 2, which means to find the area of this, it's x over the square root of 2. So this area is going to be x squared over 2, or my area is going to equal 1/2 times x squared if the diagonal of the square is in the known cross-section. Okay? So that's just a formula that we have, and hopefully you're jotting these down in your note sheets. And then we're going to come on to semicircles. Okay, number 3 is a semicircle. Well, if I have a semicircle here, here's a semicircle, and the radius of that semicircle, the radius is x, how do I find the area of this cross-section? It would be, well, I know the area equals, because that's half a circle, so it's going to be 1/2 pi, where my r is x squared. Okay, so that would be the area. If my cross-sectional area, or my cross-section is made of semicircles, this is going to be my area function a of x that I will be using. Well, how about if I have the semicircle, but now they're telling me the diameter is x. Well, we know the area of a semicircle, area is going to equal 1/2, because it's half a full circle, pi, radius squared. Well, if my diameter is x, then x over 2 would be my radius, so I'd have an x over 2. And then that's going to give me, well, that's x, this is going to give me x squared over 4, right? X squared over 4. So my area function, if they give me the diameter is x, well, it's actually going to be 1/8 pi x squared will be my cross-sectional area, or my formula to find the area of a semicircle, of an area of half a circle, given a diameter. Okay, then we're going to move on to an equilateral triangle with side length x. Well, equilateral triangle. Geometry, remember your geometry. Equilateral triangle, all sides of these are the same. They are all congruent. And if these are all side length of x, okay, well, we're going to break this down. We're going to say we know area equals 1/2 base times height. Okay, because there is a special formula, you probably had it in geometry, a special formula for the area of an equilateral triangle, but nobody ever remembers what that is, so we'll just build it really quick. So what do I need to do? Well, I know these are all 60 degrees, okay, and the area of a triangle is 1/2 base times height. Well, so I'm going to say my area is going to equal 1/2 times, I know my base is x, here's my base, and my height, remember, my height is going to be this altitude in here, and if you remember that, in an equilateral triangle, that bisects the base, and it bisects, so this is a 30-degree angle up on the top, which means this side's going to be x over 2, okay? And don't worry about that, this whole base, because what we're trying to do is we're trying to find the height. Well, I don't know if you remember this, but in geometry, again, with a 30, 60, 90 triangle, there were two formulas that came out where we said the hypotenuse equals the short leg times 2, and there was another one that said the long leg equals the short leg times square root of 3. And what do we see? Well, I know the short leg is always hitched to the 60-degree angle right here, so I know this is my short leg. Well, obviously it's shorter than the other one too. And if I needed to know the length of the long leg actually equals h here in my diagram. If I know my short leg is x over 2, right, because it's half of that, then I got to multiply that times the square root of 3, which means my height is going to be the square root of 3 over 2 times x, if I kind of break this out. So my height is going to be the square root of 3 over 2 times x. And if I put this whole function together, my cross-sectional area function, the area will equal the square root of 3 over 4 side squared. And that's how I would find the cross-sectional area of an equilateral triangle. Okay? And, well, what happens? And they're all using all these special triangles that they're going to give me. Well, what happens if I have an isosceles right triangle with legs of x? An isosceles right. Oh, I guess I just didn't serve it very well there. But something kind of special here. Isosceles right triangle. Well, that makes a very special triangle if it's isosceles and it's right. Okay, well, it's right, and if it's isosceles, the two legs are the same. So what does that make? That makes a 45, 45, 90 triangle. And if my legs are x, how do I find the area of that isosceles right triangle? Well, it's a triangle. Area equals 1/2 base times height. So the area equals 1/2. The base is x. The height is x. Because remember, the base and the height are always perpendicular. So I can make my base and height whatever I want to be in a triangle. So if I already know those two perpendicular distances, I know the area is going to equal 1/2 side squared, or 1/2 x squared. It's the same exact as number 1, except it's half of it because it's a triangle, which is half of that square. And the very last one that we have going on here is, what happens if we have an isosceles right triangle with the hypotenuse of x? Well, again, it's isosceles, which means it's here, it's right, and I know the length of the hypotenuse is x. Well, this again is a 45, 45, 90 triangle. Well, these two sides are congruent. It's a 45, 45, 90 triangle, so I can remember the hypotenuse equals the leg times the square root of 2. Square root of 2 is my multiplier in a 45, 45, 90. And I can plug that right in here. Well, if my hypotenuse is x, my leg times root 2, my leg is going to equal x divided by root 2. So I know this side is x divided by root 2, and I know this is going to be x divided by root 2. Well, how would I find the area of that little bugger? Well, isn't that going to be 1/2 base times height again, right? And we will find that. So knowing that leg, we know the area equals 1/2 base times height in a triangle. So I got 1/2. Well, if the base is x over root 2, and the height is also x over root 2, this area formula is going to turn into, those two multiply those turn into 2, so I get 1/4 x squared would be my area for these, okay? Our job here is to find some a of x function, that is my area. Find a of x that is the cross-sectional area function. That's our goal here. Our goal is to find a of x, and that a of x function is the cross-sectional area function, and we'll multiply it by a little bit of thickness, and then what we're going to get is we're going to get an integral, and we're going to multiply or add them all up. Okay? Well, what does it look like? Well, let's just say here, I have a parabolic figure drawn here. This is a parabolic region, this green one. And this is going to be some parabolic function, y equals ax squared plus bx plus c. All right? And what we are going to do is we are going to take cross-sectional area, and what we're going to mainly do here is we are going to go cross-sectional area perpendicular to the x-axis. And that's how we're going to do it. We will do one that's perpendicular to the y-axis as well. So what we're looking here for is we're going to do perpendicular to the x-axis. And in order to do perpendicular to the x-axis, bottom line, what do we need to know? Our possible cross-sections that they are going to throw at you. They are going to throw at you semicircles, which you know the area of a semicircle is 1/2 pi r squared. Triangles, you know, are 1/2 base times height. Squares, area of a square is a side squared. Area of a circle is pi r squared, okay? So let's just say we're going to draw one, or I'm going to try to draw one here for you. Let's just say we are going to do a cross-sectional area with the diameter in the region that is perpendicular to the x-axis. So what that means is I am going to have a diameter. Oh boy, I need a drawing thing here. And I'm going to make it fuchsia. And I'm going to go, my diameter is perpendicular to the x-axis. So there's my diameter. And that diameter is going to kind of look like so. And it's a semicircle. So it's also going to come up like this. And that is going to be what they are. And as these semicircles come up, they're going to get bigger for a little bit. And they're going to kind of look like this, where they have a little bit of thickness all the way across. And as those semicircles go, I'm going to have all these different cross-sectional areas. And they're going to project straight up off your paper, is what they're going to do. Okay? And they're kind of tough to draw. And what we are looking for here, okay, regardless of what we're doing, this particular one, we're just looking at a semicircle. And get a little bit to right on here, so I can scroll. And what we want to do is we want to find the volume of a single slice. I'm going to call it a single slice, okay? Doesn't matter which single slice we are doing, okay? And we know, in this case, the volume of a single slice is going to equal my area function, which in this case is going to be 1/2 pi r squared. Well, in a way, okay, my function, okay, my function is right here. Here's my diameter, okay, and my diameter is in the region known to the cross section, so we need to find the area of that cross section times just a little bit of thickness. So cross-sectional area times little thickness, which is my dx, because I'm perpendicular to the x. That's going to give me the volume of a single slice. And what I'm going to do is I'm going to go from A all the way over here to B, and my total volume is going to equal my integral from A to B of that area function times a little bit of thickness for each slice from A to B. And this is what it looks like, okay? Notice I'm a dx. This is what it looks like when you're perpendicular to the x-axis. Okay? That's perpendicular to the x-axis. Well, my diameter, okay, back here, my diameter, if I was writing out, okay, I know area equals 1/2 pi r squared. And I know r, okay, my diameter here on every slice, my diameter is that. So if I took that divided by 2, I would have the radius of my cross-sectional area. So I'd have to cut it because they gave me that as my diameter, okay? And the only thing that looks a little bit different is my total volume. If I'm perpendicular to the y-axis, the only thing that looks, ooh, that's bad. The only thing that makes it, I don't like that, I'm fixing it. If I'm perpendicular to the y-axis, the only thing that's different is my total volume will now equal my integral from C to D of some area function in terms of y, and dy is my thickness. So the axis in which I'm perpendicular to is going to dictate my limits of integration. Those will be y's, and my area function also needs to be in terms of y. That's the only difference, okay? So let's take one here. Let's look at cross-sections that are perpendicular to the x-axis are formed in the region enclosed by y equals the square root of x equals 4, and y equals 0. So you can draw this however you want, okay? And I'm going to draw my x equals 4 here quick, and I'm just going to draw x equals 4 as technically a vertical line, but I want to be, now this is going to be x equals, I'm going to label this as my x equals 0. X equals 0 is my y-axis, so my x equals 4 needs to kind of be parallel to that axis. So I'm just going to kind of come along like so. And this is going to be x equals 4. And then y equals x squared. Well, y equals x squared starts at the origin, and it's just going to come kind of through here. And this is going to be y equals the square root of x. And here is the area in which we are looking at, all right? And what I do know is the cross sections are going to be perpendicular to the x-axis formed in this area region. And my area region isn't all that great, but it's close. And there's my area region. And what we are going to do is we are going to draw in here. Now remember, this is not revolving like we have done the past week. This is just projecting vertically at you. In my cross sections, in this case, they're going to be squares whose bases lie in the xy plane. And they are going to be perpendicular to the x-axis. So what I need to do is I need to draw a couple rectangles in here. Well, you only have to really draw one. and there's my base, and it's going to kind of come up, and I'm going to try to draw my square. It's going to kind of come up like so. It's going to kind of come up, and it's going to be parallel to that, parallel to that, and it's going to come down. And my squares are just going to get bigger and bigger, where here is my side, okay? That is my base, okay? So what I'm trying to do is I need to find my area function. So what I'm going to do is I'm going to kind of come here on the side, and I'm going to look at my cross-sectional area. My cross-sectional area is a rectangle, or a square, sorry, not a rectangle. And I know the area, this is my cross-sectional area. So I know the area of a square equals my side squared. That's going to be my cross-sectional area. Well, how long is a side? Well, this is my base. My base actually equals a side. So I need to find out how long is this guy right here. Well, the length of that line is going to be my top curve minus my bottom curve. So the length of that side is going to be, each side is going to go from the square root of x to minus 0. So each side, why did I put a square root of 2? It's square root of x, square root of x, square root of x. So I know my area function, if I take the square root of x and I square it, I know my area function in this case just equals x, okay? So what I'm going to do now is I need to know my whole volume is going to equal my integral from, and I know I'm perpendicular to the x-axis, so I'm going to say, I'm going to dx, I don't need to go that wide though. I'm going to dx, so remember that dictates everything. It already gave me my area function, my side length in terms of x, that's the area, so square root of x times square root of x, and because that's a dx, I need to go from 0 to 4. So my limits are going to go from 0 to 4. And I look at that integral, and to be completely honest with you, hopefully you're looking at that saying, hey, that's going to take me longer to type into my calculator than it would be to evaluate. So when I integrate x, that's 1/2 x squared evaluated from 0 to 4. So this is going to actually give me minus here, bottom 0, thank you for that. Well, 4 squared is 16 times 1/2 is 8. So the volume is going to equal 8. They didn't give me units, so I'm just going to leave my area at 8. And what we're going to do is we are going to take this exact same area region, and we are going to calculate the volume with different types of cross-sectional area, okay? So we're going to go to the next one. And we are now going to say the cross-sections are semicircles with diameters in that region. And remember, here is my region. This is my region bounded between y equals square root of x, x equals 4, and x equals 0. But now, my cross-sections, which are, all of these are going to be perpendicular to the x-axis, they are now semicircles, okay? And I'll quit rattling, and what we're going to do is we're going to draw a semicircle. And that semicircle, cross-section is going to go, ooh, and it's going to kind of come up, and then it's going to kind of come down. So there is my area function. So as I'm looking, side, if I pull my slice out, and I say, here's my area, okay? And my diameter is in the region, I know that area equals of a semicircle is 1/2 pi r squared, okay? And whatever my radius is, okay? So what I'm looking at here is, what did they give me? Well, they gave me the whole thing. Well, what is my diameter? Well, this whole thing is my diameter right there. Okay, so my diameter is what? It's the square root of x, which means my radius is going to be, right here, my radius is going to be half of that, So my radius is going to be the square root of x over 2. So my area function is 1/2 times pi times the square root of x over 2 quantity squared. That is my area function. This is the area of a semicircle. I found my radius. So my area function, my area in terms of x, is going to be, well, remember when we squared this one out last time, that was x over 4 times 1/2. That's going to give me pi over 8 x squared. No x squared. Pi over squared x. So that's my area function. Again, I know my integral, my area, is going to equal, essentially, here is my area, and it's a dx because I'm perpendicular to the x-axis, but I would never leave that pi over 8 in there. That pi over 8 is a constant. I would have pulled him out here right away, just like that, and I would have gotten rid of him in here. So I'm just integrating, and now I need my limits of integration in there. And again, I'm going from 0. My semicircles are starting at 0. They're ending here at 4. So I'm integrating from 0 to 4. And here's another one that's going to take you less time to type into your calculator in this case, okay? So my area actually equals pi over 8 times 1/2 x squared from 0 to 4. Well, that's my pi over 8 times, well, my upper we said was 8 minus my lower is going to be 0. And pi over 8 times 8, so the area is going to be, or not area, volume, excuse me, my volume function, that's not area either. My volume equals the integral of all my area functions times their thickness, so my volume is going to equal just pi in this case, all right? Now we're going to take this exact same cross-section in the next one. And now we are going to make equilateral triangles where the base is in the plane. Okay, so my cross-section, they're equilateral triangles, and the base is in the plane. Okay, so they're always telling you which portion of the figure is actually in your plane, which means what would this one look like? Well, this one would look like, well, here's my base of an equilateral triangle. And it's going to be a triangle that comes up. And it's going to kind of come down here. I'm not going to really see that one. It's going to be a whole bunch of triangles going all the way down there. It's a little funky here, but, and I know when I pull my cross-sectional area, that is my cross-sectional area. And I can see the base of that cross-sectional area is the square root of x. Okay, so what am I thinking about here? Well, I'm thinking I need to find, this is my area function, I need to know the area is 1/2 base times height. Okay, well, that's easy. Area is 1/2 times, I know the base here, I know my base is the square root of x times, well, now I need to find my height. And my height is going to come right down here. So here's my height. Well, again, if this is an equilateral triangle, what that does is this is 60, this is 30, that's a 90. Okay, so this is my short leg. My height is my long leg. So if I think of these little shortcut formulas from geometry, the long leg equals the short leg times the square root of 3 for my multiplier. Well, do I know what my short leg is? Sure I do. Because this thing's equilateral, which means all these are the square root of x. Well, if this is my hypotenuse, or I don't even need to know that because when I drop that altitude in there to find that, it's a perpendicular bisector of that side. So I know my short leg here is going to actually equal the square root of x over 2 times the square root of 3 here. That's what the long leg is. Because I got my short leg, taking the short guy times my multiplier, which means this is going to be times the square root of 3 over 2 times the square root of x. Well, that means my area function is actually going to equal the square root of 3 over 4x. So that is my area function, and I'm going to multiply all those times a little bit of thickness. So my volume equals, I'm pulling my constant of square root of 3 over 4. I'm going to take my integral x dx, because I'm perpendicular to the x-axis again, which means my limits are still going from 0 to 4 on all of these, and I go 0 to 4, and I can integrate this thing, and my area, or my volume, should be different because these are all different figures. So this is going to equal the square root of 3 over 4 times 1/2 x squared from 0 to 4. Well, that gives me my square root of 3 over 4 times, well, the upper limit in there, again, that's half of 16. That's 8 minus, thank you, 0. So what do I get? I get the square root of 3 over 4 times 8. Well, what does that give me? That gives me 2 square root of 3. That is what my volume is if my cross-sectional area are equilateral triangles with the base in the plane. Notice their pi is not involved in this one because I have nothing. Number one, it's not being revolved, and my cross-section is not anything circular, therefore I will not have a pi involved. Okay, we're going to come to the next one, D. Now this one's a little bit different. The cross-sections are squares, but the diagonal is in the plane. Well, this is going to be kind of a funky looking one. Again, here is my area region, but now when I'm drawing my perpendicular in the area region, this one's a little tougher, that green line, that is my diameter, okay? Which means, or excuse me, it's my diagonal. And think of, we are taking, okay, that is this line right here, which means it's projecting up to a point. So it's coming up, like so. It's coming down, and it's going to kind of come in here. But also, it's projecting underneath there, which means I'm going to have that coming underneath. So it's kind of like, it almost looks like a diamond, but it's still a square in there. But now, they're allowing me to find the side of that with the square, or with the diagonal. So if I look at my cross-sectional area, it's a square. Here is what I know, and I know this line is this line. It's my diameter, and I know that's the square root of 3. No, it's not. It's the square root of x. Oh, boy. The square root of x, and I know the area of a square is side squared. Well, a square, the diagonal of a square always cuts your square into two 45, 45, 90 triangles. A square, not a rectangle, this very special rectangle, which is called a square. And I can think of the hypotenuse equals the leg times root 2. Geometry formula that's coming back to haunt you. Well, what is the hypotenuse? The hypotenuse is the square root of x, which means it's equal to leg times the square root of 2, which means the leg, which a leg equals a side of it. That means these legs are the square root of x over 2, square root of x over 2. So I can find my area function of that whole rectangle. The area equals the square root of x over 2 squared. So my area function is actually 1/4 x, right? Is what's gonna, whoa, Kruger, hold on, back up the train. I just botched that. You really gotta, probably all screaming at me there. And that's not right. And I'm dividing by the square root of 2. I could have left that, so divide by the square root of 2. So this is the square root of x over the square root of 2. Excuse me. And when I square that, hey, I get x over 2. So then that area is actually 1/2 x. that's my area region that I'm finding in there, okay, given my rectangle. So I know my volume is going to equal, because I'm perpendicular to the x, I know I'm going to be a dx. So this is going to be, I'm pulling my constant of a half out, 1/2 integral. I'm going from 0 to 4 on the x. My area function now is going to be x dx. And what do I get? I get 1/2 times 1/2 x squared from 0 to 4, which is 1/2 times, again, 8 minus 0. So this volume actually equals 4 of that one, right? And what I'm going to do is I'm going to do one more problem, and then I'm going to cut this off, and I'm going to do one more tomorrow, and then we are going to fix them all up and go from there. So here is my last one. This one is going to be cross sections that are perpendicular to the x-axis are formed in the region enclosed by y equals x squared minus 4 and y equals 4 minus x squared. Find the volume first with a base region described in whose cross sections are circular discs with diameters in the region. Oh boy. Well, first thing I need to be able to do is remember this is my x-axis, this is my y-axis, okay? And I need to be able to graph this. Well, I know that's going to have a -4 down here, and that's a bad -4, but I know it's got a y-intercept of -4, and that's going to be a parabola that is just going to kind of open a little bit, and it's going to kind of come up like this. The other side is going to come up like this, and then I'm going to have this one, which is a y-intercept, that's that, up here at 4, and then this one's going to open down, and they should be intersecting right there and right there at 2 and -2. Shouldn't take too much thought to figure that one out. And I know this one here, this is my y equals x 4 minus x squared. And this one down here, this is my y equals x squared minus 4. So here is my area region. And inside that region, we are having discs, circular discs, not semicircles, circular discs. So I am going to have a weird three-dimensional object here, but if I know this is my diameter, because they're telling me diameter is in the region, so here, bottom line, I have this top half of the circle, and then I'm also going to have the bottom half, because I won't be able to see that. So something like that. It's a whole disc, okay? It's a whole circle. So again, I'm looking here, and the diameter is in the plane. Well, I need the radius, and that is going to be the area of a disc. Well, I know the area of a disc equals what? Pi r squared. So I need my radius. I need to know what this is, okay? Well, there's a couple different ways to do this. Hopefully you are seeing some symmetry, okay? Bottom line, I'm going to come over here and I'm going to say I'm going to integrate, and I know it's going to be a dx because I'm perpendicular to the x-axis. My volume is going to equal whatever I'm coming up for an area. Well, here is my area region, right? That's my area region. Well, it's symmetrical. I can see it's symmetrical, but if I don't see all that stuff, well, my diameter is going to be top curve minus bottom curve. So that's my diameter, which means the diameter is going to equal, what did we have up there? We had 4 minus x squared, 4 minus x squared, minus the bottom, which is x squared minus 4. And that could be my diameter, and if I divide my diameter by 2, that gives me my radius now, doesn't it? So I could call it like this, and if I'm just going into my calculator, I can do that, which means I could say zippity-doo-dah, and I could say my whole radius needs to be squared, and I got a 4 minus x squared minus an x squared minus 4, and if I did that, okay, I can do a couple things here. The volume, I can go from -2 to 2, and I could find all of those, okay, except I'm going to put my pi constant out here, because I got my pi, and here's my radius squared, I needed my pi, or I can see the symmetry here, and I could also go from, 0 to 2 and double that region, and that's going to give me half of that, and then if I integrate half of it and double it, I could do that. Or another thing I could do, okay, if I'm looking right here, if this is the diameter, right, well, wouldn't that be the radius? So couldn't I just do top curve minus the bottom, which is 0? Couldn't I just say the volume is going to equal pi, because my constant is going to be in there? Couldn't I just say my radius is going to be 4 minus x squared dx, and I could go from -2 to 2, or if I didn't want to do that, come on, you pop liquor. I'm going to leave my pi there. Or I could come back here and I could go, let's say we're not going to go from there. Let's say we're going to go from 0 to 2 and then just double it, and I could do that. Well, there's another way to define, excuse me, there's another way to define that radius. I could also say my radius goes from here down to here. Well, wouldn't my radius then equal 0 minus that bottom curve, and that bottom curve is x squared minus 4, which is going to give me 4 minus, so that does give me 4 minus x squared. My first one should have been, let's see, either way, it's going to work. And, still going to be top curve minus bottom curve. And I could also say, that's fine. What was my other one I could do? X squared minus 4. I should be able to go x squared minus 4 too. It really doesn't matter. But if you did all this out right here, you actually solved your radius out from there. That's why you can do a little something different. Because if we looked at this, this is going to be 4 minus x squared minus x squared plus 4 over 2. And this is how we're getting this other part, which is going to be 8 minus 2x squared over 2, which actually is 4 minus x squared. And that's where that 4 minus x squared there in the second one kind of comes from too. But if you type these into your calculator, really you don't have to integrate this one by hand. I wouldn't waste my time doing that. It would probably be on the calculator active test. What we should be finding the volume is going to be 512 pi over 15. And notice this one has pi involved in it because it has something to do with a circle. It's a circular disk. Okay, so we found the area function. Here's my a of x, which area equals pi r squared, and my radius right here, I could have pulled from that red line right there, which is my 4 minus x squared. So the area is, should have done this first, but pi, and then we have our 4 minus x squared, that's my rate, and then I square it. So that's why this is translating right in here, and I'm just pulling the pi out, and then I went from 0 to 2 rather than negative 2 to 2. And if I'm cutting it in half using symmetry, I'm going to use my 2 pi. But it really doesn't matter which one you type in to your function. Okay? And that's it for today. You should be able to do a bunch of the homework. I'm going to do one more with this tomorrow, and then we're going to do a cross-section to the y-axis tomorrow quick. And then it should be a short video. And then you'll have time to finish up your homework, start your review. The next day will be review, and Thursday will be our test on this section. Please reach out with any questions. Have a great rest of your day, and thanks for playing math.